Now we move to calculating the confidence interval when the standard deviation is unknown. So when the standard deviation is unknown, definitely we'll use a different confidence interval. So we'll use a t distribution rather than the z distribution. Okay, and our main purpose here is how to find the t distribution. Okay, we have, as you can see, a simplified portion of the table. It's reduced here. The table in appendix B2 is, a sample or a simplified portion of it is reproduced here. So notice that the z value when the standard deviation of the population is known is given by this, x bar minus mu over sigma over radical m. However, when the standard deviation is unknown, of course, we're going to estimate the standard deviation of the population with the sample standard deviation. So instead of sigma, we will use S as an estimate of the population standard deviation. So the t value is x bar minus mu, okay, which is the mean of the population, over S over radical m. Okay, where S is the sample standard deviation and is used to estimate the population standard deviation when it is unknown. Great. Now, as you see, the t distribution has the following characteristics. First, it is like the z distribution. It's a continuous distribution. The z distribution is a continuous distribution. We have already talked about it. Second, it is like the z distribution, a bell-shaped and symmetrical. This is the bell-shaped and symmetrical. Okay? From 0 all the way to the right is the same as from 0 to the left. So they are symmetrical. They're equal. Okay? It is bell-shaped like the z distribution. As you can see, the z distribution is thinner than the t distribution. All t distribution have a mean of 0, as you can see. But their standard deviations differ according to the sample size n. The standard deviation differ according to the sample size n. The t distribution is more spread out and flatter, as you can see. This is the t distribution, is more spread out. That is, the standard deviation is bigger, of course, than the standard normal. However, they have the same mean, okay? As the sample size increases, the t distribution approaches the standard normal distribution. So always we're going to assume that we have a standard normal distribution for when we're talking about t distribution. The formula for the confidence interval when the population standard deviation is unknown is given by this. So this is the confidence, this is the formula of the confidence interval when the population standard deviation is unknown. So it's equal x bar plus or minus t, which is the t distribution, times S over radical n, where S is the sample standard deviation, which is used to estimate the population standard deviation. To determine the confidence interval for the population mean with unknown sigma, we, use the following three things or conditions. First, we assume the sampled population is either normal or approximately normal. So whenever we're going to use the confidence or calculate the confidence interval for the population mean, we're going to assume that the population is normal or approximately normal. Second, we're going to estimate the population standard deviation with the sample standard deviation. So when the population standard deviation is unknown, then we're going to use, instead of the sigma, which is the population standard deviation, we're going to use the sample standard deviation, as you see in this formula over here. Okay? So we put sigma, instead of sigma, we put S. Use the t distribution rather than the z distribution, okay, when, of course, the population standard deviation, of course, is unknown. Now, so we have to use the t-distribution rather than the z-distribution when the population standard deviation is unknown. Of course, we're going to assume that the population follows a normal distribution or approximately normal distribution. And of course, we're going to also estimate the population standard deviation with the sample standard deviation. Now, how to calculate the t-value? Given below a simplified portion of the t-distribution from Appendix B2. Now, as you can see, this is a simplified portion that is reproduced here. This, table of the t-distribution is much bigger than here, okay, than this one here. And so this is a portion of it. Now, the question is that how we use this one to calculate the t-distribution. For instance, remember, as you can see over here, the confidence interval, you have 80% level of confidence, you have 90% level of confidence, you have 95% level of confidence, you have 98% confidence, level of confidence, and you have 99% level of confidence. These are the level of confidence that are in the table. Now, and you have level of significance for one tail test, of course. You have level of significance for a two-tail test. And then our main concern here is the degrees of freedom. The degrees of freedom here, okay? Where the degrees of freedom is equal the sample size of the sample size minus 1, okay? So df is equal n minus 1. So if the sample size is 20, then the degrees of freedom is 20 minus 1 is equal 19, and so on and so forth. So here, I'm giving an example. Say n equal 11, and the level of confidence is 98%. Okay? So what we do first? Well, first we calculate the degrees of freedom. We come up with 10. This is 10 over here. Okay? Now, we have the level of confidence is 98%. The 98%, where is it? Here. So now what you do, I move along the row to the right, all the way, okay, until, I hit the column with the heading of 98%. Then it's going to equal this value over here, 2.7684. This is the t-distribution. It's this is the t-value, 2.764. Right? So that's what you do. This is the value that the intersection of the column with 98% and the row with 10 degrees of freedom. Let's say, for instance, if n equal 10, okay, and the level of confidence, level of confidence is, let's say, 80%. Okay? Then what you do first, how to calculate the t-value? First of all, we calculate the degrees of freedom, df, which is equal 10 minus 1, which is equal 9. Great. Now we go to 9 degrees of freedom here. As you can see, we move down. Where is 9? This is 9. Okay, then we move horizontally, okay, in the row with the 9 degrees of freedom until we hit the level of confidence, 80%. What is 80%? Here. So this is what you get here, 9 degrees of freedom, and then we come here. This is the value. Okay, it's 1.383. So it's going to be t is equal 1.383. Okay, this is the t value. So we have 9 degrees of freedom, and then we have 80% level of confidence. So they intersect here. 9, we move here, 1.383. And you can calculate, of course, the t values for other level of confidence, whether 90%, 90%, 95%, 98%, or 99%. It's very easy. All you have to do, find the degrees of freedom, and then the corresponding level of confidence, whether 80 or 90 or 95 or 98 or 99, and then the value that you will find for t is at the intersection of the the row of the degrees of freedom, okay, and the column of the level of confidence, and you come up with the value as I show you over here. Okay, now what we do, we just try to give some examples applying, the confidence interval, applying the formula of calculating the confidence interval of the population mean when the standard deviation of the population is unknown. Okay? I just want to correct something here. This question is, I'm just resolving this question or this example, because perhaps the previous solution, a very small error took place. So now I'm just going over the question again to show you that this question is solved by using the formula of the confidence interval of the population mean when the standard deviation is unknown. However, previously I did solve it assuming that the population mean is known. No, it is not known. So I'm just solving this question again, by using the formula of the confidence interval, when the population standard deviation is unknown. So that formula is different. Here, when the population standard deviation is unknown, then we use the formula of the confidence interval is that x bar plus or minus t times s over radical n, where s is the standard deviation of the sample. Now, this is the question. A cookies factory is concerned about absenteeism among its workers. To determine the mean number of absent days in the population, a sample of 10 workers was selected and studied during the last 2-week period. The sample shows an average of 1.8 days absent with a standard deviation of 1.1353. So here, as you can see from this example, we don't have the standard deviation of the population. We do have the standard deviation of the sample. Therefore, since the standard deviation of the population is unknown, then we have to use a different formula of the confidence interval. So the first part, or the first question of this exercise is that determine the sample standard error of the mean. The sample standard error of the mean, of course, we did calculate the standard error of the mean of the population. Of course, here the sample standard error of the mean is that s into x bar, which is equal s over radical n, where s is the standard deviation of the sample. So we have it here, 1.1353. We, of course, divide that by the radical of the sample size, which is n, and we come up with 0.359. So this is the sample standard error of the mean. Determine the margin error. Determine the margin error. Of course, the margin error. The margin error E at a 95% confidence interval or confidence level. Of course, E is that equal T S over radical n. T times S over radical n. Of course, here we use the, the distribution T rather than Z. Why? Because the standard deviation of the population is unknown. So this is the margin error is equal T times S over radical n. Of course, to calculate T, we have to go to the table. We have already talked about it, how to use the T distribution from the table in the appendix, of course. First, we have to find the degrees of freedom, DF, degrees of freedom, which is equal to n minus 1, which is, we have 10, 10 minus 1 is 9, and then we go to the table of the T distribution table, and then we come up with T equal to 2.262. I have already talked about how to use the T distribution table. Okay, so we come up with T equal 2.262. Great. Now, therefore, substituting the values in E, we come up with, of course, the margin error is equal 0.812. This is the margin error. Now, determine the 95% confidence interval for the population mean. Okay, great. The confidence interval, because the confidence interval formula is this: x bar plus or minus t times s over radical n, or x bar plus the margin error, plus or minus the margin error. Okay, so we come up 1.8 x bar, which is 1.8, plus or minus 0.812, 0.812, which is this one here. So this is actually the range, the interval between 0.99 and 2.612. This is the range. Now, would it be reasonable to conclude that the population mean is 1.5? Of course, as you can see, 1.5 is within this range. Within this range. Therefore, yes, it would be reasonable to conclude that the population mean of 1.5 is within the range or inside this confidence interval. Okay, now we move to, of course, exercise 2. Exercise 2 says a simple random sample of 10 students is selected from college A. For the 10 students, the number of days each was absent during the last semester was 3, 7, 2, 1, 0, 2, 4, 2, 6, 2. So, a selection of 10 students, and we are after finding the number of days each student was absent during the last, of course, semester. Of course, the first student is 3 days, the second 7 days, the third is 2 days, the fourth is 1 day, the fifth is 0, he never miss a class, and the sixth is 2 days, the seventh is 4 days, the eighth is 2 days, the ninth is 6 days, and the 10th is 2 days. Now, question A, find the sample mean and the sample standard deviation. Now, of course, these from previous chapters, okay? Already discussed the sample mean and the sample standard deviation. However, we can repeat the way to calculate the sample mean as well as the sample standard deviation. Of course, the sample mean we represented stands for by x bar, which is equal the summation of x over m, where this sigma, capital sigma, okay, it stands for summation. So summation x over m, okay, and we come up with 2.9. We add all those numbers, absent days, and we divide by 10, we come up with 2.9. And this is, of course, the sample mean. Now, the sample standard deviation this is the formula here. The sample standard deviation, of course, this is the formula. Of course, we have to implement this formula the sample standard deviation is the square root of sigma x minus x bar squared over the n minus 1. So implementing this, of course, we start with absent days. This is the value, this is x. This is the variable x. This is the mean, 2.9. So what we do, first, we have a heading of x minus x bar. Okay? So 3 minus 2.9, 7 minus 2.9, 2 minus 2.9, all the way. Okay? We come up with this. The summation of x minus x bar will always come up with 0. Okay? The summation is 0. Summation is what? Is 0. Always the summation of x minus x bar, x the variable minus it is mean, of course, is equal the summation of x minus x bar is always 0. Now another heading of x minus x bar square. So what we do, we square all those numbers, okay, calculated in the previous heading over here, and we come up with what? These values. So the summation, we add them all. Summation of x minus x bar squared is going to equal 42.9. So when we x minus x bar, for instance, 0.1 squared, we got 0.01. 4.1 squared, you get 16.81, and so on and so forth. And we add all of them, we come up 42.9. Okay? Now, we plug all summation of x minus x bar squared over in this formula, sample standard deviation. We plug them, we come up 42.9 square root of 42.9 over n minus 1 over n minus 1, and we have 10 minus 1, 9, and we come up with 2.18. We come up with 2.18. So the sample standard deviation is 2.18. Now, what is the best estimate of the population mean? What is this called? Of course, the best estimate of the population mean is the sample mean, which is called the point estimate. So the sample mean, we just calculated it over here, is the best estimate of the population mean. Great. Now, should we use the t distribution or the z distribution? Why? Of course, as you can see, we don't have the population standard deviation. We did calculate the sample standard deviation. And the sample standard deviation is going to estimate the population standard deviation. And since the population standard deviation is unknown, then we have to use the t distribution instead of the z distribution. So we use the t distribution because the population standard deviation is missing, is unknown. Now, find the value of the test statistic. Of course, in this case, the test statistics, in order to use the t distribution table, of course, we have to find the degrees of freedom. And degrees of freedom, of course, A is equal n minus 1, which is equal 9. So we take this 9 degrees of freedom to this t distribution table, and we calculate the t value. The t value, of course, at the 95% confidence interval. Okay, I have already talked about how to calculate the t value using the the t distribution table. So as you can see, at the 95% confidence interval, of course, it says the question at the 95% confidence interval, CI confidence interval, construct the confidence interval for the population mean. And this is the formula solution: x bar plus or minus t times s over radical m. Of course, here as you can see, t times s over radical m is that this is, of course, the margin error. This is the margin error that we have already calculated this in the previous question. And we plug the numbers over here, and we come up with the range or the confidence interval at the 95% confidence. At the 95% confidence level is going to be equal 2.9 plus or minus 1.560. This is the range, or this is the interval. Now, would it be reasonable to conclude that the population mean is 4.1? As you can see, 4.1 is inside this range. Is inside this range. You know, the lower limit of this range, 2.9 minus 1.560. And the upper limit of this range is 2.9 plus 1.560. So as you can see, 4.1 is within this range. Okay? Yes, it would be reasonable to conclude that the population mean equal 4.1 is inside this range because it is located inside the range. Yes, it would be reasonable to conclude that the mean, the population is 4.1 because it is located inside the range. Okay, now we talk about the confidence interval for a proportion. What is a proportion? Of course, proportion is the percent, ratio, or fraction indicating the part of the sample or the population having a certain attribute of interest. So this is what actually we mean a proportion. And here in this section, we're trying to find the a confidence interval for a proportion. So a proportion is the percent or ratio or fraction indicating the part of the sample or the population having a certain attribute or characteristics of interest. Now, an example of a proportion, for instance, a recent survey of undergraduate students in a small college in southern England indicated that 20 out of 100 surveyed favored the continued use of online to deliver classes. So here we're talking about, this is an example of a proportion. You have a 20 out of 100. So the proportion is 20 over 100 or 0.2 or 0.20, or 20%. In this example, the sample proportion is 20 over 100 or 0.20 or 20%. So we can represent the proportion either in fraction or ratio or in a percent. Sample proportion is going to be, written in this formula. Rho equal x over m. So the sample proportion is going to be represented by rho equal x over n, where x is the number of successes and n is the sample size, and rho represents the sample proportion. So the sample proportion is equal x over n. So for instance, over here in this example, the sample proportion is 20 over 100. Remember that to develop a confidence interval for a proportion, the following assumptions must be met. So in order to develop a confidence interval for a proportion, of course, we need certain assumptions. These are the following assumptions. First of all, the binomial conditions have been met. What actually we mean by binomial condition? Of course, we mean that, let me just state some of them. We have already stated them when we talked about discrete random variable in a previous lesson. We said, that a binomial assumption consists of certain, characteristics or certain assumptions. First of all, the random sample counts the number of successes in a trial, of course, in a fixed number of trials. We have two possible, outcomes, a success and a failure. The probability of success and failure remain the same for each trial, and that the trials are independent. That is, the outcome of a trial does not affect the outcome of any other trial. So this is some of the assumptions of a binomial distribution. Now the second, of course, assumption that needs to be presented or to be met is that the values n pi and n into 1 minus pi should both be greater than or equal to 5. Of course, this condition here invokes the central limit theorem, which actually employed the standard normal distribution that we calculate the z, which is important in order to use the confidence interval. So here, this condition, it invokes the central limit theorem and employed the standard normal distribution where we calculate the z, of course, in order to use the confidence interval. Now, the confidence interval for a population proportion is given by the following, formula, which is rho plus or minus z times the square root rho into 1 minus rho over n. Okay, this is the confidence interval for a population proportion, for the population proportion. Now, let me, of course, apply this formula, of course, in order to understand the details of using the confidence interval for a population proportion. This is the example. Mr. Khalid is considering running for mayor of his town in Egypt. He decides to conduct a survey of voters in his town. Of course, a sample of 500 voters reveals that 380 would support him in the election. Now we have 3 questions concerning this problem. First question says, estimate the value of the population proportion. Estimate the value of the population proportion. Second, develop a 90% confidence interval for the population proportion. Third, interpret your findings. So, solution. Okay, first, let's answer the first part of the questions. Part 1. To find an estimate of the population proportion, we need to calculate the sample proportion using this formula over here, O equal x over m. Okay? So now we just plug in that formula the values. We get here 380 over 500, we come up with 0.76. Okay? So therefore, we estimate that 76% of the population would vote for him in the election. So we say that an estimate of the population proportion is going to be the sample proportion, which is 0.76. This will estimate the population, proportion. Now, second question, develop a 90% confidence interval for the population proportion. We're going to use this formula up here. Okay? Now, using the formula which is up here, rho plus or minus z into rho into 1 minus rho over n. Of course, the z value, of course, is important. That the z value corresponding to 90% level of significance is 2.58. Is 2.58. Of course, we have already talked about that, how to find the z value using the z table. Of course, when you have a standard normal distribution, I will come up with z 2.58. Now we plug this one in the formula. After plugging all those values, we get rho 0.76. We have already calculated the rho, which is the sample population. Plug that in the formula. We get 0.76 plus or minus, of course, plus or minus 2.58 into 0.76 into times 1 minus 0.76 over 500. And then after, simplifying, this calculation, of course, we'll come up with these, this interval, 0.76 plus or minus 0.0492. Of course, the confidence interval is between 0.11 and 0.89. So now this is the confidence interval calculated using the formula of the confidence interval for a population proportion written up here. Now, the question number 3, it says interpret your findings. How we interpret the findings? Of course, we say that we are reasonably sure that the population proportion is between 71% and 80.9%. So we are sure that the population proportion is between, more than 71% and 80.9%. Okay? So here, just to note, the population proportion is denoted by pi. That is, it refers to percent of success in a population.